our goal is I can apply combinations of transformations. So this is actually almost the last of transformations. There's one more lesson after this dealing with a slightly different topic. Okay, so here is the equation that demonstrates all the different transformations that we can deal with. Okay, now it's really important to understand that the order of transformations is important. So you just can't do whatever you want first. So it's something like order of operations in the sense that we have to follow certain rules in order for that to occur. And we'll just bring this up for you. And we'll get some color. Okay, so stretches, compressions, and reflections occur before translations. So stretches, compressions, and reflections. So let's take a little closer look at exactly where those items are. Okay, so here's this general formula. So when we look at the letter A, the variable A that's in front that we're starting with. Okay, that tells us a few different things, that A. First of all, it tells us whether we have a vertical stretch or compression. So if we put a number 2 or a number half in there, it stretches the Y values. It also tells us whether we're reflecting something into the X axis as well. Okay, so if it's positive or negative. The next item that we would look at would be the K value. Now the K value, remember, affects the value of X. So what's happening here is with the K value is it tells us the horizontal stretches and compressions. So what this is saying to us when order is important, that we need to do the compressions and stretches and reflections first before we do the horizontal shift, so in other words, left or right, and the vertical shift, which is up or down. So in most cases, the one that we do first is the horizontal stretches and compressions, so how it affects X. Then we look at the other items in a specific order, and then these two here can be done together in most cases. So let's look at a couple examples when we're actually doing this. Okay, so what we have is describe the order of the transformations and then graph the following functions. So the first one, f at x is 1 over x. So we know that it's the reciprocal graph that we're looking at, and we're to apply the transformations to it. So if we look at first, what we should do is remember we want to look at our compressions and items here. So if I look here, I'm not changing, there is the value for the horizontal stretches. This K value in this case is 1. So I'm not changing horizontally. However, I am changing the vertical stretch here. So my first would be the vertical stretch. So it would be done first. And then what we would do is we could actually apply the other two together. We could actually apply then the horizontal shift and vertical shift. So we're going to, in this case, horizontally move it to the right 3. So horizontal shift to the right. And we also have a vertical shift down. Okay, so these two, the horizontal and vertical shift, they don't have to be done in a particular order between the two. So in order to now graph this function, I'm going to start with the parent function. Okay, and we know this parent function, we should know that it has asymptotes along the x and y axes, and we should know the step pattern of it. So that's the first thing that we're going to draw, is that, and let's just take that, and I'm just going to move my recorder over a little bit if it will move so it's out of my way, but I can still see the time. So straight line, dotted, and let's make it light green. So we know that we have an asymptote there, an asymptote here, and if we go to graph it, we know that it's over 1, up 1, and then it's a creeper graph. Okay, now it's not a square graph here. It actually has a curve to it, and then it creeps along the axes. Okay, so that's my parent function, which is f at x. Now, by putting that 1/2 in front, that's going to affect my y values. So what I need to do here is I need to go over 1, but instead of up 1, I'm only going to go up 1/2. So that's what we're going to do. So I will use red in this case. It's going to go up 1/2. The same thing here, I'm going to go to the left 1 and down 1/2. Okay, so what we end up with is a graph that looks very, very similar. The only difference being is the distance between the asymptote lines. So now we've done that, and now we need to apply the horizontal shift and vertical shift. Okay, so we know that in this case, we are moving horizontally 3 units to the right. So that means I have a new asymptote line there, and we will use, let's use purple or blue. Can't even tell colors correctly. Here we go. So there is that asymptote line, and then down 2. Okay, so we have 2 new asymptote lines, and we can do the same thing with our value here. We could actually take that point, move it to the right 3, 1, 2, 3, and then down 2, 1, 2. Sorry, did I get it down 2? Down 1, 2. Sorry, it's because it's at 1/2. Just going to get rid of some of that. So it's here. And then the other one, the same thing applies to it. We could actually take it and move it over 3, 1, 2, 3, and then down 2. So 1, 2. So we're going to put a point there. Okay, and so now we have our 2 points, and so now we want to apply the same kind of creeping kind of thing. And this is our g of x. Now, when we're just applying a vertical stretch, we could probably get away with transforming our horizontal and vertical shifts and then apply the vertical stretch. The only real issue occurs when we are doing a vertical stretch and a horizontal stretch. Okay, so that's something that we need to watch out for as well. Okay, so let's do one more question. I think we can get it in our time. All right. Our f at x this time is the square root of x, and our g of x, you can see there's a few things going on here. Okay, so what would I have to do first? Well, according to what I said before, we would have to do this first, which is our, oops, it disappeared on us, which is our horizontal stretcher compression. So in other words, we're changing our x values here. So the horizontal stretch. Okay, and we're going to take a little closer look at that in a moment. I'm just going to put a star there. And then we also have a reflection here. You can see the negative in front. So then we would do our reflection. And finally, we would do our translation, our horizontal. translation of 3 to the left, and also our vertical translation, which would be up 3. Sorry, up 4. Okay, so before we actually get working on this, I'm going to draw our parent function, which is the square root of x. Now we know that that pattern starts at, just going to use one of these lovely little ones that we've had before, and we'll make it smaller. Okay, so we know it goes at 0, 0, then it goes over 1, up 1, over 4, up 2, it goes over 9, up 3, and we could go further and go over 16, up 4. Okay, so this is our parent function. Okay, so I'm going to put our parent function, and it has f at x. Okay, now what we're going to do is remember, when we're talking about horizontal stretches or compressions, we multiply, it's the reciprocal. So here we have 2, so the reciprocal of the 2 is 1/2. So 1/2 of the x values. So in fact, it's going to take us half of the x values to get as far as this 3. Okay, so it's going to take everything by half. So now what we're going to do is we'll do this one in green. So it doesn't affect this point. This point stays the same. But now if I go over 1/2, I would be up 1. If I go over, instead of 4, if I go over 2, I'm up 2. So I'm taking all these x values that we have at these important places and cutting them in half and getting the same y value. So the next point would have been over 9 up 3. So I'm going to go over 4.5 up 3. The next point, remember, we said would be over 16 up 4. So I'm going to go half of 16 is 8. So over 8 up 4. Okay, so what we've ended up here is we have graphed, this particular one is going to be f at 2x, is what we've just graphed. And so we have completed the horizontal stretch. Now we have to do the horizontal reflection. And so we're going to reflect all those points down. And so I'm going to stop the video and we'll complete this one so we don't run out of time.